Hello, everybody, and welcome to this week's workshop at the University of Ethereum. My name is Rachel, and I'm your host for today. I am joined with an amazing guest. We have the co-founder of Polygon on today, Jordi, which I'm so excited to get into some ZK tech today with Jordi. Really happy to have you on, man. And yeah, I'll go ahead and pass it off to you to start with your introduction. Jordi's got an incredible founder story and has done some amazing work at Polygon. So yeah, Jordi, I'll pass it off to you and would love to hear your introduction.
Thank you, Rachel. Glad to be here. And well, let's start. I'm, as you said, well, you mentioned, I'm Jordi Baylina. I'm the co-founder of Polygon. Before being co-founder of Polygon, and well, before everything, I'm a developer. I'm an engineer. I'm a developer. That's very much what I like to do. I'm a developer since I'm 12 years old. I'm in the crypto space since 2015. I've been in many adventures. I've been a white hat at the beginning. I learned a lot of Solidity. I did some audits at some point. Then later I get a lot of interest in the ZK technology. I wrote Snark.js and Circum back in 2017, which is very much used today in most of the ZK applications. And then we created identity project, it's Ident3, among other things. And from there, we just joined forces with Polygon 2 years ago. And since there I'm one of the Polygon co-founders, and I'm the technical lead at ZK VM and doing a lot of ZK work inside Polygon. And yes, the idea of today is to introduce a little bit this technology, the ZK technology, which is amazing, and we will see that's very, very useful and very trending also in today's, and we will see in the context of the blockchains and in the context of decentralized systems, more generic, how this technology impacts, and see how important is this tech for the future. So let's start. As I mentioned, first I'm going to introduce a little bit what's the zero knowledge. Then we will talk about how we apply this technology for scaling blockchains and why is that important. Then we'll talk a little bit about the privacy and how these technologies helps to understand and the privacy. And finally, we are going to do a little bit of overview of other applications that can be where this technology can be used. Okay. So yeah, this is when we are talking about zero knowledge. In general, we are. So it's just the same tech, but actually are two big applications, two different applications, and even the way of writing. Even the way of using this technology is quite different when we are talking about scaling and when we are talking about privacy. There are two applications that are very different, and but you will see that the technology is the same, but actually is the mindset is very different. Okay, so let's start first about scaling. Scaling is, if we see the problem of the blockchains, why blockchains do not scale, and if we go to when Bitcoin starts, scaling has also been the main subject. The main challenge for these decentralized systems to work and actually to go mainstream. Many tries have been doing, the Lightning Network and the state channels and Plasma at the beginning, and it was not until the zero knowledge appears in the space that actually this scalability problem was, I would say, fully solved or solved in a nice way. Okay, so why blockchains do not scale? Okay? Well, blockchains, as you know, is a consensus system. Consensus means a set of nodes that they need to agree to something that's common. In this case, is a block. So in the case of Ethereum, every 12 seconds there is a block that's a consensus. That this block is the block number 20,000 that includes these transactions and only these transactions, and the state of Ethereum goes from here to here. Okay, and there is a consensus for that. Okay, but in order to compute this node in a consensus way, they need to process. All the participants on this consensus, they need to compute. They need to, before agreeing to a block, they need to verify that this block is valid. Maybe somebody proposes, but maybe somebody proposes something that includes some signature that's not correct, or that you overspend, or you double spend some of your funds. So not all blocks are valid. There are consensus rules that needs to follow, and everybody in the consensus needs to check that. If there is 1, 2, 3 transactions every 12 seconds, no problem. I mean, any computer can handle that. But if there is thousands of transactions, then processing all these transactions, there is a bottleneck. I mean, in one side, well, we can ask users to have bigger nodes. This is, for example, what's doing Ethereum compared to Bitcoin. I mean, the requirements of the Ethereum node is much higher than the requirement of a Bitcoin node. Or you see other networks, the computer is, I mean, you see Solana, it's a huge computer compared to Ethereum, or even Polygon. I mean, the Polygon POS, the computer that you need to run a POS validator is higher. Okay, but there is always going to be this limitation. I mean, it's how big is the computer. If you do if you put here a supercomputer, it's going to be not very decentralized system, because maybe there is only 2, 3 supercomputers that are just managing the network. And if you do a small requirement computer, then the system will not scale. I mean, the quantity of transactions you will be able to do is not possible. And that's because all the nodes, they need to process all these transactions. Okay, so this is and getting the consensus. I mean, this is the biggest bottleneck in there. Okay, so with that in mind, let me explain you zero knowledge, what it is, in a very simple way. Okay, so a way of understanding zero knowledge is what we can call a verifiable computation. Imagine that we have a program, a deterministic program. When I'm saying deterministic program, is a program that just do one computation, that you give an input, you compute something, and you get the output. But if you run the program again, you're going to get always the same output. For example, I don't know, you do a program that adds 2 numbers. You get the input 2 numbers, and the output is just the addition of 2 numbers. Or you get solve this polynomial equation. Okay, so the solutions of these polynomial equations are this and this. If you are trying to solve that again, you're going to find always the same solutions forever, whatever complex is that. Okay, and with this program, so imagine that so you and me, we both have we know this program, and I just run this program. Imagine it's a program that takes a week in a supercomputer to do this computation, in a very, very expensive computation. You can imagine, for example, I don't know, a training of some AI, AI training system, or computing a huge hash, or something that's really hard to compute, something that takes a week in the biggest computer in the world. Okay, I do the computation, so I just run the program. Okay, I just run the computation. I give the result to you, and okay, it says this is the result. But if you want to check that result is valid, what you do? Well, the obvious thing you do is you run the program again. Okay, so that means that you just take this supercomputer, you spend 1 week more, and then of course it gives the same result. Okay, the result that I give to you was correct. Okay. But imagine that there is a tool, there is a technology, there is a system that what I do is, okay, I do this computation. Of course, I need to spend this week doing this computation. But besides building this, besides computing the result, I also build a cryptographic proof of this computation. That means that when I give you to the result, I give you to you also this proof, and then you just checking that this proof with this result is correct. You can check that this computation is valid, but instead of doing that in 1 week, you do it in few milliseconds. And the cool thing of this technology, of this proof, is that no matter how big is the computation, the time it will take to check this result is going to be constant, very few milliseconds. Okay, so this is very much what's a zero knowledge proof. Actually, this is what's a computational proof. Zero knowledge is a little bit more, because actually zero knowledge means that I don't even need to give you the input of, I mean, the input of the circuit. I just give you the output. I will put some examples there. Okay, but Zero knowledge, especially in the context of scalability, means that it's a verifiable computation. I do a computation, I generate a proof of this computation, and I can give you the result and the result of this computation, and you can verify that this computation was valid in a very few milliseconds. Why is this important in the context of the scalability? Well, the thing is that when we are running a consensus system, so imagine that somebody, some miner proposes a block, some proposer proposes a block, but all the nodes, instead of having to verify, to compute all the transactions and to verify that this block is valid, the proposer also gives with the block some proof that this block is correct. So that means that the people in the consensus, they just need to check that this computation is valid. Actually, this is done in Ethereum in a smart contract. In a smart contract, you can verify in one smart contract any computation. So you can verify a computation in a smart contract. Okay, and the cost of this verifying this computation is relatively slow. It's around 300K gas. And no matter how long is this computation. Well, but that's very much what's a roll-up, and that's why this technology is important to scale. When we explain now what's a roll-up, it's mainly is just using this zero knowledge, is building these systems where you don't need to prove, you don't need, so you just prove, you don't need to verify. So not all the people need to verify, just all the people, in this case in the Ethereum network, they just verify the zero knowledge proof, and with verifying this, they verify the huge computation on that. Okay. So this is the part for scalability, and that's why it's important for the zero knowledge to scale. Just to mention here that to scale, this is not to scale blockchains. This is not enough. In the case of the rollups, you also need what's called the data availability. But here is where Ethereum is doing an amazing work here with all the dank sharding and all these EIP 4844 blocks. This is very much the goal of the layer ones currently. They are focused very much in scaling the data availability part, because then the rollups can do the other part of verifying this computation. Okay. Zero knowledge. This technology, just a brief recap, but this technology is a technology that's relatively old. It was invented in 1985 by Shafi and Mikhaili in Berkeley. From there was I would say it's a very theoretical concept, and was not until say 2008, 2010 that there were some important research and a lot of papers that at that time that introduced the concept of a non-interactive proof. So it's as you generate a proof and then everybody can generate. Before that, the zero knowledge was also interactive. If I wanted to prove something to you, it was a dialogue between you and me. Okay, and at this point, this dialogue is just I'm sending you the proof and that's it. Okay, so that's an important advance that happens by the time, and other important techniques and discoveries that happens during 2005, 2010 that comes from there. And in the context of blockchain, I think it's fair to mention the Zcash work. Actually, Zcash was the first blockchain that brings this amazing technology to the blockchain space. It was for privacy, not for scalability at that point, but it's important to mention there. Okay, and from there, a lot of researchers, people, and this is a technology that just explodes in the last years. Okay, so here all the tooling. Right now this is a technology that's available to any program. At the end of the presentation, I will share some links. But if you search, there's plenty of information and plenty of examples, tooling to work with this ZK deck. Okay. Here I'm going to go a little bit fast, but right now there is a bunch of different zero knowledge schemas. There is still a lot of research moving on, and it's quite a huge ecosystem. A lot of the systems, depending on the systems, have different advantages and disadvantages. Depending on the application, maybe it's good to choose one or the other. Okay, but I'm going to share here what we are using right now in Polygon, and I would say that this is probably what it's not all in Polygon. I would say that most of the projects are using. Okay, so here there are many, but this works very well. The idea is zero knowledge based on the Starks. I mean, Stark is it's a zero knowledge system. It was invented by Eliben Sassoon and a long time ago, and I mean it's a full proving system that's very, I mean, it's fast to compute. It has all the advantages. I mean, it's fast to compute. It doesn't require a trusted setup at the beginning. One thing is you can do recursion very well. You just need to, so the primitive that you're using is hashing. I mean, the only problem that has this protocol is that the proofs that generate, they are quite big. Okay? And if you want to prove that on chain, they are very expensive to verify that those proofs on chain. So the technique here is, so we are using a Stark for building the proofs. We can have a lot of Starks. We can aggregate a lot of the proof in a single proof. I mean, you can have a proof that actually is proving two proofs. This is very much what's called aggregation or recursion in proving. And you can think, for example, in the case of the ZKVM, is like you have a single proof that actually proves many blocks. Each block is a subproof, and then each block inside the proof, you can have other subproofs in there. Okay, so when you're proving things, is you are doing this kind of Merkle tree or kind of Merkle. So you're just taking all the proofs and you're converting them to a single proof. Okay, you do that in a Stark. And when you have a single proof in the Stark, then what you can do is you can verify this proof that's a Stark with a Snark. Okay, so you do a proof for proof too, but in this case you are using other proving systems like Grow16 or Flonk or Plonk or others that are much cheaper to verify on chain. So you just work with the Stark. This works very well for everything. And the last minute, in the last moment before sending on chain, you just convert it, or you just verify it with a Stark. So you just send the proof of this Snark of this on chain, and then it's very short. It's a proof. In the case of Grow16 or Flonk, the proof is very short, and it's very cheap to verify on chain. Okay, so this is, I would say, this architecture is the one that most of the projects are using, because this gets the best of each proving system. I mean, there are some here to mention that there are some improvements and details. I mean, GKR, for example, is used for doing some pieces, especially when you are connecting many Starks together. There is some techniques, and even the way to building that, there is a lot of research that's going in that way. But I would say that this way of doing proofs is the one that's used in today's day, especially for big circuits. Okay, so if we go a little bit on detail, I mean, it's what's in kind of a roll-up. Well, this is the idea. I mean, we can understand, if we understand how a blockchain works, is very much you start with the genesis block. I mean, this is a current state, and then you get different transactions. So you just to build the block, and then you get to the next state. This is the block number one. Okay, you get more transactions, you go to the next state. You go more transactions, and you go to the next state. Okay, so a blockchain can be understood as a kind of a state machine. So you go from one state, you process some transactions, you go to the next state, you process some transactions, you go to the next state. Okay, so the circuit that you are actually proving is very much that. So you are just taking the current state, and then you prove that when you apply these transactions, you go to the next state. Okay, so and in the case of the rollup, it's very much is a kind of a smart contract, where in the smart contract you just save this state, and there is some operator somehow that's creating new states, each state with each proof that's each state with each proof that's saying that this state is correct so that the transactions are valid. Actually, in this smart contract, in general, there is also the data availability attached to here. So it's like, okay, you have this data, which contains a lot of transactions. And when you apply this data, when you apply these transactions to the state, then you do this state. And then you can build a full chain that there is some operators that are just building these new states, okay? And you know that these states are going to be valid. I mean, you cannot overspend. And actually, in the case of the ZKVM, well, the idea is that this state transition function is the same that Ethereum. So you get, you can build transactions. You can do these transactions in MetaMask. You send them to these operators, and they are included in that state. And then the proof is generated that this transaction is correct. So that means that, well, as you can see, this circuit, this program that you want to prove is quite complex because it's the Ethereum itself. I mean, it's a program that just takes some transactions as an input. They process these transactions in the Ethereum way. I mean, they emulate those transactions. They compute the new state, and they verify that this new state actually is. So this computation is, if you process these transactions, then the state deterministically that you get is this one. Okay, so this is what you are proving. And that's why, and this is just, I mean, in the smart contract, you just send the new state. Well, you send the data, you send the new state, and you send the proof of the new state, and the smart contract just verify that this new state, that this proof is valid, and then this new state is what is mixed. Here is in general is attached a bridge, so you can deposit from Ethereum back and forth different funds, and this is very much what's the ZKVM, what's a rollup it is. Okay, so and this is why it's important this zero knowledge. Okay, but we can go a step further. Okay, and this is very much what we're building in Polygon. In Polygon right now, we are building what we call the aggregation layer. So it's like we don't have a single rollup, we don't have a single chain, these layer 2 chains on there. The idea is that we can have like many chains running. Okay, so we can have here chains can be public chains, private chains, chains with one token, chains with another token, chains that are different. So all sorts made. I mean, we can have different. You can imagine that anybody should be able to run their own chain. Okay, and the problem is that when you have a lot of chains, if you just put them standalone, then here is I mean, it's relatively. So they get like silos. I mean, the chain has its liquidity, it has its funds, and then transferring funds from one chain to the other chain is I mean, it's hard because I mean you need to go to the bridge, you go to layer 1, and this can take some minutes or even hours to move from one side to the other. So the idea of this aggregation layer is the idea is that all these chains, they are sharing a set of rules, okay, and they connect to this aggregation layer. So the idea is that they can transfer funds from one to the other, or they can transfer value messages. I mean, they can work as a single chain, but they go in a fast way. I mean, imagine that the chain that is, I mean, you are just maybe the ZKVM, a generic chain that is trying to to buy something, to buy maybe a travel plane that's in a company that's building another chain, and maybe in the same transaction you have also an insurance company, so you want to build a transaction that's a conditional transaction that you are buying both things at the same time in a kind of an atomic way. How you do that? Okay, because the idea is that in the aggregation layer you can do that. You can have like different chains run by different consensus or different individuals or whatever. I mean, some private, public chains, they are different chains, but the idea is that you can move. The idea is that you can transfer this information from one chain to the other. Okay, and what you need to do, I mean, if you go to the detail of how you do this transfer, okay, well, the idea is so when I want to transfer, imagine that I'm chain A, okay, and I want to transfer something to chain B, okay. Well, chain B, so when chain B can consider that that the funds on chain A has been locked somehow, or they are transferred to chain B. If I'm in chain A and I transfer something to chain B, chain B needs to be sure that this transaction is executed in chain A. What cannot happen is that this transaction, you say that this transaction is executed, chain B takes these funds, maybe you spend something in there, and then there is a kind of reorg in chain A, and then these funds are not changed. So they need that first they need a commitment of the state. So the chain A needs a way of committing, okay, this is the new state, okay? But chain A could fake that. I mean, could do some tricks. I mean, they can commit maybe to an invalid state. So here is where the zero knowledge is important. Actually, chain B has like two options. One is, okay, I'm going to include these these transfers or this new state from chain A, because I'm running a node at chain A, or all the validators of chain A are running a node on chain B. They're running a node on chain A, which doesn't scale very well, or just chain A just emits one zero knowledge proof that this state is valid. So you get a commitment, you get that this state is valid, and then in chain B you can start using those chains. Okay, so and the commitment here is that the new state is valid. Okay. And the cool thing here is that this proof of the state transition of each chain, actually in the aggregation layer, we're splitting in two pieces. Okay, so actually there are two proofs. One proof is what we call the state transition function. Is okay, you are a chain, and then you are doing. I mean, this chain has some rules, the rules of the own chain, and you are guaranteeing that when you're running this chain is correct. Okay. And then we have other rules that are the rules that are the rules of the aggregation layer. It's what we call this pessimistic proof. I mean, this is the minimum requirement proof that all the chains needs to do in order to connect to the aggregation layer. And these rules are very much that each chain cannot send more funds to the other chains than the funds that they have. So these guarantees, maybe there is one chain that's corrupt. I mean, imagine one chain that's a centralized service. There is even no state transition function. Just somebody that's saying, okay, the funds belongs to him, the belongs to them. Okay, you can have a very, let's say, low security chain. Okay, well, this is perfectly possible. You can connect that to the aggregation layer. But this aggregation layer cannot affect other chains. You can in the funds that are in your chain, do whatever you want in your chain, but you cannot. Spend more funds than the ones that are assigned to your chain. Okay, and this is what guarantee. I mean, this is the co-living rules of all the chains. It's okay. A chain can do whatever they want. They are quite sovereign. I mean, they're quite autonomous. They can have like different systems, whatever. But of course, if you move to one chain, you need to trust that chain. Okay. But if you are in chain A and happens something in chain B, you should be. If you are in chain A, you should be safe. Okay? And this is what's guaranteed with this pessimistic proof. I mean, it's this minimum set of rules that you need to guarantee, and that's very much doing this accountability, this chain level accountability, that the chains are not spending more than that. Okay, and this is when you are transferring from one chain to the other. Well, you need to commit to a state, and you need to be sure that this state doesn't change, and that this new state transition function in most of the chains and this pessimistic proof are correct. Okay? And you want to do that fast, because I mean the idea is that if I'm a user and I want to do a cross-chain transaction, I want this to happen fast. I mean, I want to send the transactions, and in maybe 5 seconds, 10 seconds, I get the result. Okay, and in order to do that, we need to build zero knowledge, these zero knowledge proof that are huge in a fast way. Giving you some numbers right now in the zkVM, building a proof for one node is about 2 minutes in a big machine. But the idea is that we can do much better than that. Okay, and this is very much where we are working. We can parallelize a lot this proof computation, and the idea is to be able to do these proofs in a block time. And I think this is perfectly possible. And then this is from the user perspective is going to be really amazing, because I mean you should be able to build to do these interchain communications. So in the future here, for example, app chains are going to be quite common and easy. What it was before, mean, what was 2-3 years ago, what most of the people, they were thinking in creating their own layer one, and a lot of projects, they end up building their own layer one, and this is so crazy. So right now, I would say that the future of the blockchains happens by, you create your app chain. In your app chain, you set up your rules, whatever you want. You connected them to the aggregation layer, and then you are connected to the world. You have all the liquidity, you have all the functionality of the other world, but you have your autonomy in your own chain. This opens a lot of new business models, and because your own chain, you can charge for the fees, and you can have again your own token. You have the consensus level, the sequence level that you want to have. You define what you need in your chain, and then you connect to this aggregation layer. And this is the project that we are working hard right now in Polygon, and I think this is the future of the blockchains. How they will scale and how they will work. Okay? And this is very much thank you to this zero knowledge, that this speed of transferring and this of transferring funds between chains, that what allows us to grow fast. Okay. We have been talking till now about the scalability. You see the importance, have seen the importance of the zero knowledge tech, that it's in the blockchain space, especially for scalability. But talking about zero knowledge, I don't want to forget about talking about privacy, because actually privacy was the original, would say that's the oldest application in the zero knowledge, comes more from the privacy. And privacy is, you can call it privacy. Sometimes you want to hide information, or the other way to do is do some disclosure. You want to show some disclosure information. Okay, so but there is many ways to understand that. Let me just explain. Let me just explain this diagram. Okay, this is what the self-sovereign identity is. Okay, and this is, you will see the importance of that. Okay, so imagine that you have a database. So a way of understanding the world is a database of claims or a database of attestations. What means that? So imagine that every time that happens something, you do an attestation. It's like if you go to a notary and you do a statement. For example, you are doing a course in the university, and then you get a degree, and then the certificate for the degree. It's like they go to a notary, they do a degree, and then you have like a kind of a proof that you have a degree. Okay, so this statement, that the university says that you are an engineer. This is a claim. Okay, this is a statement. Okay, and you can understand the world. So anything that happens can be a claim. Okay, so you can imagine I don't know. I'm connecting to a web page. This is this can be a claim. A debt recognition can be a claim. That I'm working in a company can be a claim made by my company. That I have a COVID certificate is a claim. That I have a hunting permission can be a claim. So everything, so any action that humans or even non-humans are doing in general with other objects, with other identities connected, this can be a claim. Okay, so you have a set of, say, identities. You can understand identity as a public-private key. You can have you get a public-private key. This is kind of an identity. Maybe it's an identity that represents yourself. Okay, and then you have this database of claims. Maybe the government saying that this identity belongs to Jordi, that was born in Barcelona, that plays. All the state can give you can emit a set of claims. Okay, so we have a database of claims. Okay? This database of claims is decentralized. So depending, the university will hold some claims, but I also hold some claims that, these claims that I'm a student. So this database is a shared database. It's the kind of a decentralized database. Not all the information is everywhere. Each user holds like part of the information. Actually, it holds the information that's related to you, either because I'm an issuer and I'm generating claims. If I'm a government, of course, I'm keeping in my database all the claims that I'm emitting. But if I'm a user, I'm also getting my claims. I mean, maybe these the degrees that I have, and maybe some medical information, medical data, and it's something that I hold myself. Okay? This is the idea of self-storage, is that I hold my information, I hold my things of proof. Okay, and we have this huge database. Okay, and we have these users, this public-private key. Well, the idea is that I can prove things. Okay, so for example, the identity holder here, so here it is the issuer, this can be the university. The university just generates these these claims. Okay, as it shares with me that I'm an engineer here, but then I can use this information. The idea is that I can prove to a company that I have this degree. Okay, or say the other way, the company can ask me to prove that I'm really an engineer. But somebody can ask me that that I have a hunting permission, or they can ask me if I have whatever information I can prove me that I have a KYC or whatever information I KYC it somewhere, or that I'm a person with some certain reputation of a certain degree. Okay, and the cool thing here is that you are just so you are just proving a yes, no. I mean, you are proving. I mean. So you don't need to send all the information. You don't need to share that information. You are just sharing the information that you are required. Let me put an example, for example, in insurance. I mean, when I'm applying to an insurance company, the insurance company in general is asking me about all my medical records, if I apply or not apply. So I need to give him the full information. With a zero knowledge proof, the idea is that I can just, okay, I have the information, I hold my information, it's my medical information, so I hold the information somehow. Okay, so I can generate a proof that according to the medical information that's signed by the doctors and so on, that's part of this database, the trusted database, I can prove that I could apply to this insurance. But the medical information that I'm sharing to these insurance companies, just a yes, no. A yes, like you can apply, you follow certain criteria, or no, you don't follow the certain criteria. Okay, so the cool thing here is that with zero knowledge, we can prove, we can select it, we can prove some specific things. I mean, we can do queries to this database, to this decentralized database. We can do some queries on this database and prove that those queries are correct. Okay. And this is done because actually you have some information. You have this database can be hashed. I mean, somehow this is hash or a set of hashes that are in general the top root of these hashes are in the blockchain. Okay, they are stuck in there. But this hash can be millions of claims that are in a tree according to that hash. I mean, to this database. So I can prove things according to these anchors. Okay. And I can prove these things according to these decentralized or to this set of decentralized database to one to the other. Okay. Identity systems, these are very important. Okay. And the cool thing of this is, and just talking a little bit about the identity here, is that so until now, all this zero knowledge, this is what's, so until now, all this zero knowledge, they were quite specific. And if you wanted to prove things in the zero knowledge, you needed to use, in a practical, if you want to do that in a practical way, you need to use some strange cryptography in general. I mean, you needed to use baby jab, specific, very strange hash functions, and so on. And all the identity protocols that were around, the IDs and so on, they were not think with zero knowledge in mind. Okay, and this was quite hard to connect one with the other. Okay, currently with the current ZK tech, the current state of the art of the ZK. Right now, doing ZK proofs are relatively cheap. It's getting lower, and what's more important, they are becoming kind of commoditized. So writing these programs, I mean, if you see, so writing these deterministic programs, until now, you need some specific tooling for doing that. I mean, it was very expensive to do, and you need to be very optimized, and then you need some specific tooling. Okay, here to mention Circom, for example, is in this one of these tools that you can use for that. But you need to write the program in a specific language in order to fulfill some arithmetization. I mean, it was hard to do. Okay, but in today's work, every time this is writing one of these zero knowledge is going to be just as easy as writing a normal program. Just take open Rust or C++ or whatever. You just run a program and then you prove that computation. It needs to be deterministic, so you need to have an input-output. You cannot use randoms, or you cannot easily use randoms, and that's it. And this is becoming quite of commodities. Here, important to mention here projects like ReZero or SP1 and others that are coming, where you should be able to use this. This is still, all these technologies are still, I would say, in the last stages of development. It's still a little bit expensive to build those proof, but this is getting lower in one side because the protocols are getting better, but also because there is some hardware acceleration that's happening right now. And this is one of the trending topics that are happening in the ZK space right now, this hardware acceleration and some new techniques for accelerating these things. But in any case, proving a general purpose Rust program, a quite complex Rust program, that's like, and this is in the digital identity. This is becoming very important. I mean, this is becoming very important because you will not need to use special protocols or special cryptographic systems or special formats. And adapting to current digital identity systems is going to become much easier. Here, for example, having a circuit that passes a JSON and extracts a signature and analyzes that signature is perfectly possible. And I mean, this is what Polygon ID is doing, is just trying to leverage all these new technology that happened here, that happened in the last 2 years, the improvements that happened in 2 years, and try to bring them to the digital identity systems by connecting to the current protocols itself. Here, and just to finish the presentation, let me talk about other things that are super interesting from the zero knowledge, for the zero knowledge perspective. One of those, for example, is voting. Anonymous voting is an important, thing that can be done with zero knowledge. So decentralized, having decentralized voting, massive scale, you can combine the privacy part of the voting together with the scalability for having massive voting. This is a lot of interesting things happen there. Here, maybe to mention projects like Bogdoni or other projects that are working on that direction, that I think is good to have. Auctions, blinded auctions where you can bet and then prove that what you are betting is correct and things like that. There is a lot of applications there. Gaming, when you are doing an online gaming, decentralized gaming, there is, you want to play poker online without having a centralized system. Well, you can prove that the moves or the things that you are doing there are correct. Here, mention, for example, some pioneers like Dark Forest game at some point, but games like that, it's right now, it's an important industry that happens there. But other things that are interesting in the zero knowledge, applications for fighting against fake news. You have maybe a picture and you want to prove that that picture was taken in some places, and the processing filters that you see there are not manipulative. It's a real picture. I think that's one of the examples. Or proving that, proving the sources. You just prove that the sources are correct without revealing the sources. Other applications that I think that are a little bit futuristic, but I think that are perfectly interesting. For example, one thing you can do with this tech is, for example, pay taxes without having to reveal how much you pay it. You just prove that you pay it what you had to pay according to some rules. So this avoids, for example, many people in the administrations having private access to your information on that. This, you see, I mean, there is others. I mean, we can talk about, for example, I know that one interesting application is fishermen's, that they are proving that they are fishing in the right places without revealing the exact place where they are fishing, so they cannot reveal this information. But there is, I mean, there is a lot of applications, some of them privacy related, maybe some of them are more scalability related, but there is a huge number. I mean, AI, there is a lot of applications based on AI. I mean, there is a lot of applications that happen to this technology. This technology is becoming very, 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 very important. If you are interested on that, here is Rachel will share here a lot of some links and contents, but again, just Google, go for it, try it. Maybe just one good example is you can go to the Snark.js. Snark.js is a tooling that we built in 2017, but just a tutorial there. I mean, if you're a developer, you can just spend half an hour, you run the tutorial there, and you will see how you create a full circuit, you build the proof, you verify that proof on chain, and you can see the full cycle of how these things work. I think this is very inspiring, very motivating, and at least to understand how this at block level, how this works and get your hands dirty is something that's interesting. And again, a lot of things, this new technology, so the tooling is becoming very commoditized and very available, and it's a lot of things that needs to be built right now. I mean, it's a moment where there's a lot of applications and a lot of opportunities that happens because this technology is available.
Yeah, just wanted to say, Jordi, thank you so much for taking time out of your busy day to come here and teach students at the University of Ethereum about ZK. To anybody listening, to students or anyone that stumbles across this video, this is one of the leaders in our industry, you guys. This is someone who truly is an expert. Jordi, you could be teaching this stuff at a university, just such a comprehensive wealth of knowledge in this presentation. And I do want to ask some questions before we close here. So the first thing that came to mind when you were giving your presentation, okay, privacy. I know in the US, that is something that has been somewhat controversial. There were a lot of privacy projects that came about. A lot of them were, had to pivot or change their focus because in the US, I mean, with the SEC having an all-out war on crypto, they're not too, keen on privacy. So what do you think is kind of like a good balance for projects to prioritize privacy of their users while also being compliant and not putting a target on their backs?
Well, that's where zero knowledge is can give value. I mean, until zero knowledge worked, it was a trade. It's always a balance. It was a balance between I either have privacy or I either have security. I mean, I want to live in a world with less terrorists and less people with less money laundering. And I want to give away some privacy, or I want to live in a world that has more privacy, but there is more risk for these bad things to happen. And we were in a balance in there. The cool thing is that with zero knowledge, we can have both things without having to renounce to one of those. So I can still keep privacy, and with this proof, actually I can prove that I'm not a terrorist, that I'm not a delinquent, that the money that I'm using is right money. I can prove that I'm KYC. When you go to a bank, for example, I mean, a bank don't care at all who you are, what's your name, where you live. I mean, they want just to put your money there. Or you go to an exchange. I mean, you want to trade. The exchange for you to money is okay, just put money there and just exchanges. They don't care about who you are, where the money comes from the business perspective. They care because there is some government that's asking them to get all this data, to get all this information. Because there is some concerns and there is some security. I mean, it has good reasons for them to ask them. Okay? But with this technology, the idea is that we can convince the government, we can convince the law enforcement, we can convince the people that the things that we are doing are correct, but the exchange don't need to hold all this information. They need to hold, not to hold all this data. They just hold out the proofs that are correct. So you can keep the privacy. I mean, you can. Privacy is a human right. I mean, you have the right to have privacy. You don't want to. So imagine that all the bank accounts are shared. So all the transactions that you do in your bank account is valuable. I mean, you want privacy. We will not get. So blockchains are not going to work until this privacy is solved somehow. Privacy is needed, and this is not incompatible to give the guarantees that the things are done for the right way and the right thing. And you can use the zero knowledge, do the selective disclosure to prove whatever you need to prove, whoever, in order to work well. And if we use this technology in the right way, we can have a much better society. We can have a system where we can have privacy, real privacy, at the same time that we have security on there. And yes, this is a technology. A technology is, the good thing of technology is that allows humanity to get better without having to be in this balance. We just break the balance. Why we need to renounce one thing if we can have both? But again, I mean, we need to build that.
Awesome. Well, wow, this is just such an innovative and important technology. I just appreciate you taking the time to go through it on such a deep level, because it's something I know for us non-technical folks, it can be a bit daunting. But yeah, I mean, a couple things you brought up. I mean, I'm really fascinated in the aggregation layer, because that actually sounds like it's in line with the ethos of EdCon and Ethereum, right? Building an interoperable future. I mean, I think that's one of the reasons you're going to make such a great speaker at EdCon. Like, that really is one of our themes this year. Another question I had for you also was, what can attendees expect to see from you? Because you actually are going to be a speaker on the main stage this year at EdCon. Can you kind of tease a little bit what attendees can expect to see and learn from you at EdCon this year?
Yes, I mean, of course, all these aggregation layer. I mean, all this interoperability, connection between chains and how they connect with each other. This is going to be probably, I would say, if not the main topic, at least one of the main topics, if not the main topic that we are going to talk about, and how these chains connect, what are the guarantees. I mean, this is an important thing to talk about. If we go a little bit deeper in the ZK space, well, here we're going to talk about the ZK technology. What are the last advances? What are the last news? What are what we can expect, and actually how this technology is going to explode, and also how this will affect to many applications. I mean, there's a lot of things that will change things. I mean, from the user perspective, for example, having a full wallet. I mean, a full trusted wallet, for example, in the mobile phone. This is something that's going to happen in the coming years. Kind of a light client, full ZK light client. This is, for example, a super interesting application that can happen. But there is a lot. All these the chain communication. Of course, this is very important. But it's a lot of things that are moving forward. Of course, probably here we'll talk a lot also about the data availability that I mentioned a little bit before, but it's a lot of topics that are happening, and EdCon is definitively one of the top conferences, if not the top conference after the DevCon that happened during the year. And yeah, I would say that there is where we will see how the state of the art of this the Ethereum world is in there.
Absolutely. Awesome. Well, Jordi, we're so excited to have you back as a speaker. I mean, you've been a speaker of EdCon before. I've seen previous videos, and you just do such a great job doing these technical breakdowns. And yeah, it's really needed in our industry. We need folks like you breaking down these things, exploring what's possible for these technologies. And, all the students, all the people watching here, I mean, the intention of these workshops is we want to encourage your curiosity. We want you to go out, get your hands dirty, and try and build solutions to these problems. So, Jordi, I would love to close with some resources for how students can get involved, how listeners can get involved, and how they can build on Polygon.
Yeah, I mean, of course, you can join at the Polygon blockchain and the blockchain Polygon webpage. I mean, there is a lot of links and a lot of documentation on that. I would recommend, especially for developers, that go to the GitHub repositories. I mean, if you're interested in something, just go deep and just read the code, just read what's going on, get your hands dirty. That's that's important. Here is one of the some of the Trusted is one of the competitors of Polygon, but here is a lot of amazing zero knowledge resources that are there. Just Google, just go there, get deep, get your hands dirty. You will definitively get. I mean, if you are a developer, you're going to enjoy a lot. And if you are come more from the business and more from just trying to change the world, understanding this technology and what's possible with this technology, you will see that there is a lot of things that can be done to improve the society. So just very inspiring to read all these and understand what's behind, and just take the part that you are interested and build something.
Awesome. And then the last resource I'll share, shout out to Dabl Club. I actually co-hosted an event out here in San Francisco with Colin from Dabl Club, and it was so much fun. Yeah, shout out to Colin too for giving me this rare Polygon hoodie, which I love. It's my favorite piece of Web3 clothing now, favorite swag. Yeah, Dabl Club. So they have started, I mean, you could probably give a better explanation for me, but the impression I get is that they're trying to encourage more builders to come onto Polygon, right? So do you want to kind of give high-level explanation of Dabl Club and how folks can get involved?
Just just go there and join. There's a lot of funders there and a lot of opportunities. And in Polygon, I mean, at the end, it's an infrastructure level, but you can build on top of that. And definitely, it's a lot of resources, a lot of people that you're going to find there. So yeah, join there.
Awesome. Now, okay, final question. I like to ask this to attendees as we close out. If you could give any parting words of wisdom, right? Like with the University of Ethereum, we work with students, we work with blockchain clubs and universities around the world globally. So what would your parting words of wisdom be to the next generation of builders?
There is many things to share here. First thing is, I mean, if you are a developer, just get your hands dirty. I mean, that's the thing. The only way to learn this, I don't know any developer, any good developer, but I would say, I mean, every developer that has not gone, it's not a self-teaching person, a person that gets curiosity, that goes there, try things and learn things, and it's it's an autodidacta person. I mean, that's the important part. The other part that I want to say, and that's something that's, I mean, it's a little bit more philosophical, but just be sure that you understand what we are building here, okay? Because this is, so this idea of common goods, this idea of what we're building here is systems that they don't belong to anybody, but actually they belong to everybody. I mean, they are common goods. I mean, they are like the air or like the roots or like things that anybody can use it. They are just there. Anybody can use it. Nobody can stop them, and nobody can break it. And it's just a value that's for humans. Okay? And this was not possible, at least in the IT industry, to build things like that until now. Open source projects start somehow in that direction. I mean, you can have a Linux operating system at some point, but no, I mean, we can have money, we can have a full, voting system, we can have a Scroll smart contract there, we can have some insurance, decentralized insurance there, we can have a lot of decentralized applications, a lot of decentralized services, and understand these decentralized systems that they don't belong to anybody, including yourself. I mean, they are just things that they are just there, they just work, and you just, as a user, you just can use it, and you can take profit of that. And this is what we are building, and we cannot forget about that. Understanding these core values of a decentralized system. If we forget about these values, maybe we're going to use the technology in a nice way, like any other technology, but we will not use the main differential value that this tech have. So that's what I would tell them, and just understand what they are building and where is the value that they are adding to the society.
Awesome. Well, Jordi, thank you again so much for taking the time today. We really appreciate you over here at the University of Ethereum and the EdCon team. I mean, we're so thrilled to have you as a speaker. We have Polygon actually hosting an event at the United Nations University in Tokyo. So there's going to be an ag cave. It's going to be really exciting at the academic arm of the United Nations in Tokyo. So yeah, there's a lot of exciting things planned for EdCon, and we hope to see you there. Jordi, looking forward to meeting you in person. And again, thank you so much for taking the time today.
Thank you.